Now that we have simple commands, let's see if we can implement piped commands. And in order to do so, we're going to need to understand the pipe system call. Before we get into pipe, though, let's establish where we're at and set up a diagram of what we're going to need to accomplish in the next part of our lab. So we've got a process here. I'm going to name P0. That is a process of the THSH, the Tar Heel shell. Right? So this is our THSH process. And this process, when we begin it, we're waiting at the terminal, or we're waiting at standard input for some input, and we're about ready to, let's imagine we had entered a piped command, and where do we go from here? All right. Well, before we get into that, let's establish our file descriptors for this process. Right. So our process P0 is going to have file descriptors 0, 1, and 2 corresponding to standard in, standard out, and standard error, right? And this is going to be a table, right? And so these values are going to, the actual entries for each of these numeric process descriptors is going to be associated with some file in the operating system. So I'm going to set up the file, or remember we think of this as just IO, input output stream table in the operating system. All right, and the operating system is going to have an entry for the terminal that we're connected to for reading. And so I'm going to say that standard output is for, and let's just call this TR, and terminal is what we'll describe this as. And then standard out is terminal for writing. And then the standard standard error is also going to be attached to the terminal for writing. All right. Great. So we've got our tables set up here, and this is at the operating system level. And I'm going to make a quick note of that as well. All right. So this is the operating system, and this is our process 0. So when we get a command, I'm going to change colors for our command here. All right, so let's try using blue for this command. Let's say the command is something like ls, and then we're going to pipe ls into grep for the letter C. Right? The resulting parse tree of this, right, is going to be a pipe node. And it's going to have two children, right? A left child, which is going to be a command node. And that's going to be the ls command. And it's going to have a right-hand side, which is another command node, which is going to be the grep command, right? So the question is, when we go to execute this tree of commands, how is it that we are going to evaluate it step by step, right? So let's think about this and try and imagine what it is that we're going to need to do before we go and implement this program. Okay, so we are going to process this node tree step by step, and let's start at the root. At the root here, the first node that we encounter is this pipe node. And when we encounter a pipe node, we should probably handle that. We should set up a new pipe. All right, so we're going to make a pipe system call first. And this is our first time seeing the pipe system call. So what does it do? Well, when we call pipe, the operating system sets up a couple of new entries in its file table, right? We have a pipe read end. So this is a pipe read. And each time we call this, there would be a unique pipe read end set up, right? So this is just this would be its own unique thing here that would be separate from any other pipes. So this is our pipe read. And we're going to also have a pipe write that gets set up as a part of this, right? And then the process is also going to be, its file descriptors are also going to be extended with those two descriptors. So it's going to have at by this example, we'll assume that the integer values are 3 and 4. We'll learn that whatever these two numbers are that are the processes handles on this descriptor would be returned back to us by the pipe function call. So they might not always be 3 and 4, right? Like if we were setting up multiple pipes, they certainly wouldn't be. But let's just assume they're 3 and 4 for now, and 3 would get the pipe read end. I'll just do PR, and 4 would get the pipe write end, right? And so now we have these two file descriptors that if we were to write to 4 or read from 3, we would be reading and writing to this pipe in the operating system. We've made this connection, right? And maybe I'll just label these pipe. Right? So we've set up this pipe, right? And the reason why we need to do that first is when we go to then process the subsequent commands of spinning up a child process for ls and spinning up a child process for grep, we're going to need to give these file descriptors to them in order for them to know how to overwrite their particular standard input or output to connect up to this pipe, right? Okay, so we've handled this pipe, and now what do we do next? Well, I'm going to change colors again, and let's say we use an orange here for the next part for this ls command. All right, so next we're going to look at this ls command. So we're going to work left to right as we move through our tree. So the pipe was established as part of processing this pipe node, and now we're ready to go process this command node. All right. And what are we going to give to that command? Well, we're going to need to give to that command some context about this pipe, right? And we'll see that there's a little bit of extra context we're going to need to give to it as well. But when we go to process this command, what we're going to do is we're going to fork, right? So ultimately, when we process a command, we know that we need to fork. And when we fork, we create a child process, right? And when this child process is created, before it goes to execute the ls command, we need to get its table set up correctly. All right, so what happens when we fork? Well, remember, when we fork, we get a second process out of it. So now we're going to have P1 here. And P1 is going to have duplicate entries for all of these file descriptors initially, right? So I'm going to copy these over. All right, so it's going to have standard input will still be connected to the terminal read end, output to the terminal write end, error to the terminal write end, and then file descriptors 3 and 4 will be for the pipe read and the pipe write. Okay, so this happened automatically as part of that fork process, and we're still connected to these same backend file entries in the operating system's file table. Okay, so we learned about the dupe command or the system call in the previous lecture. And what that allows us to do is actually establish the correct connections in process ones or our child processes file descriptors, right? Because we want, if we're piping the output of ls to the input of grep, then that means we want to change the standard output of P1 to be our pipe, right? We don't want it to be the terminal that we're writing to. We want it to be the pipe's write end that we're writing to, all right? So we're going to need to make a call to dupe2, right? And what are we going to do with dupe2? Well, we're going to overwrite, we're going to take the pipe write and assign that to standard out, right? So we would take file entry number 4 and say, hey, make file descriptor entry number 1 be the same as it. So effectively, process 1 is going to have PW as its entry for file descriptor 1, which is its standard output, right? So we called dupe2 to override, and I'll just make a note here for standard out. All right. The next thing we want to do is close the read end, right? So we're not going to be reading on process 1's pipe. So we're going to close the read end of this pipe just to be a good citizen here, right? So what we want to do is this. So we're going to close the read end of the pipe, right? Okay. And now we're ready to say, okay, we've set up our file descriptor table. And we want to hand off control to this ls command, right? So we want to hand off control to ls. So what do? Well, that's when we call the exec function, right? So we're going to exec ls, right? So that's going to be the exec system call, and we're going to exec the ls command, right? So this would be us processing that. Great. So that's forked for this child. Now, one of the interesting things about forking and executing a command is this is all happening. We don't necessarily know the exact sequence in which these two processes are going to run. And I should make a note of this is P1, which became just now the ls process, all right? So the parent process, P0, our shell, still needs to go fork our child. And I want to pause right here to give a conceptual introduction to something that's important to understand. Notice that all of this could have happened before we began the grep function. We could have begun running ls before grep was started up. And why would that be okay? Well, we're writing to this pipe, right? And that pipe can fill up. And when that pipe fills up, because no one is reading it yet, that will cause the ls program to pause right there, to wait until it can write more data to the pipe, right? So each time you call write, it's checking to see, hey, can I even write? Is there space in the buffer in this pipe for me to write to? And if not, it'll pause that process. All right, so what else does the shell process need to do? Well, now that we've processed the left-hand side, let's go process the right-hand side, right? So I'm going to switch colors to green here, and let's process this command grep. All right, so let's assume now that we are going to fork again. All right, so we're going to fork again for this grep command, and I'm going to draw this arrow by jumping over this one. All right, and now we're setting up a process 2, which is currently still THSH, right? We haven't yet run the exec command that would cause that process to be replaced. We know that when we fork, we get a copy of our file descriptors from the process that we forked from. So this copy is going to come from P0, right? Because we forked from P0. Okay, so let me enter these in really quickly. So this would be the terminal read end, the terminal write end, the terminal write end, the pipe read end, and the pipe write end. Okay, so these were duplicated from P0. And now we want to do like effectively the same sequence of steps we did for the ls process. We need to do for the grep process to set it up to be executed. But we need to be sure that we're careful in connecting our pipes in the right way that we expect, right? So what do we need to do with this dup2, right? So we're trying to, once again, make sure that our standard output of ls flows into the standard input of grep, right? So in other words, we want standard in for process 2, this where we're currently reading from the terminal, just on how this was set up by default, we want that to be reading from the pipe instead, right? So what we would do is we would say dup2, and we would give 3, which is the pipe read file descriptors ID, and overwrite file descriptor 0 standard in, right? So standard in for process 2 is going to be the pipe read end, right? So PR is what we're reading from on the pipe, all right? And then we also want to be good citizens and close the right end of this pipe. So we would close PW, right? Because we don't need the right end of this pipe here. And then we would go and we would exec the grep command, right? So we're going to exec grep and give it whatever arguments it needed, right? So now this is no longer THSH, this is now grep. Okay. All right. So these programs are now running. They're communicating with each other. Grep, when it has output, is going to be writing to the terminal. It's reading its input from the pipe, and the ls command is writing its outputs to the pipe. So these two things are connected these two processes are connected via a pipe. Now, what are we doing back up in our parent process, the shell program that we're writing? Well, we want to be good citizens and close this pipe that we're no longer using, right? So this pipe is no longer open in our process. So we would close the read end of the pipe and the write end of the pipe in our parent process. All right, so we're going to close these two things. And I'm going to change colors to red and just indicate which of these ends we're closing out. Okay, so we've closed out you, and we've closed out you and you. All right, and the key thing that we want to be sure of is just that the pipe is, while it's open and while we're reading and writing from the two ends of the pipe in each of these processes, only one of these processes after this is all set up should have one of them open and be able to read or write from it. All right. Now that we're back up in the P0, what we want to do is we want to wait on these processes to complete. Now, we're not going to get into the details of wait in this course. I mentioned to you that we're giving it an argument of null, which says just wait for any of my children to finish and to complete. But one thing that we need to know is that when you wait, as soon as a single child is exited or completed, it will return from that wait call and continue on in the program, right? So the first time we wait, I'm going to assume that the ls command or the ls process was the first of these two processes to wait. That would cause we wouldn't continue on from the first call to wait in our parent process until after ls is process completed. But we also need to wait again. So we're going to need to wait the same number of times as there are children processes which we spin up. If we want to do this in a blocking way, which we are, we would want to wait again. All right. And then our program would continue on and ask the user for another command after we've completed all of these things. Right? So this is the strategy that we're going to follow for setting up a pipe, spinning up a child process for the write end of the pipe, spinning up a child process for the read end of the pipe, and then waiting on both of those processes to complete before we prompt the user again for another command. Right? And the good news here is that this strategy can be followed by effectively taking our tree structure here and first doing the work that we need to do on the pipe, second, doing the work we need to do on the left-hand side of the pipe, and then third, doing the right-hand side of the pipe. Now, I want to point out that this command could be more complicated, right? We could have had another pipe here instead of a command that was made up of two more commands, and we would have needed to recursively apply the same process. And what that means is when we return back from any node, we're also going to need to say as a return value back up from our execution strategy, how many children are we waiting on, or how many children does the parent need to wait on, right? So we're going to need to return that information back up as we are recursively descending down this tree. The information we're going to return back up is how many times will the parent process need to wait in order to know that all of the children have completed, right? And so in the case where we have just two nodes in this command nodes in this tree that we're waiting on, we would just have two. But again, if we had a command where, let's imagine this were another pipe, and we had another command here and here, how many will we be waiting on? Well, this would return 1, this would return 1, and then pipe is going to return the sum of those two sides, right? So that would return 2, and then 2 plus 1 would give us, we're going to need to wait on 3 commands or 3 processes to finish up in that example, right? So we're going to need to structure our the functions which process a tree of nodes in a clever way that allows us to do two things. One, we're going to need to get that information back from those function calls. How many processes does the parent need to wait on? And two, we need to pass, as we're moving down into the recursive parts of each of these commands, we're going to need to pass in some context. And the context that we're going to need to pass in are some instructions about like, hey, process 1, here are the file descriptors you should use for standard input and standard output. And what we're going to do is tell process 1 from our parent, like use the pipe right end to be your standard output. That's what's going to give it the inclination to call dupe2 on that particular descriptor. And then we're also going to need to say, here is the descriptor that you need to close that you're not going to make use of. right? And the same thing for process 2. So let's actually resolve some of those details in code and jump into code now.